now we're recording. Okay. So yeah, that's perfect. Especially because sometimes, when I was talking about programmers kind of losing sight of the point, and us getting so geeked out about like the algorithms and like the problems, like again, using TSP as a toy problem for evolutionary computation. But sometimes we go the other way, where it's like, no, this very formal, well-defined mathematical problem has some very obvious, very important real-world applications, like how to distribute cell towers, right? Where they can't have the same company having so many towers in certain areas, so it's like graph coloring. So there's a perfect example of where this is a good implementation of what this means in real life. But can anyone tell me, like, did anyone spend some time thinking about what a good representation might be? No, that's okay. I never really told you to. But you know what? Maybe, do we have class Thursday or tomorrow? Next class, for next class, I want you to just think about it. Don't come up with anything crazy formal. Don't write down pages of ideas or anything. Just think about it. Let it brew in the back of your head. If you're watching baseball tonight, who's watching baseball tonight? Oh, come on. The Jays are in the play. Oh my gosh. Well, they're in the running for the wild card spot, and the Yankees are ahead of them. Damn AL East. The Yankees are ahead of them, but they got a 3-game series against them. If they win the series, they're going to be in the playoffs. It's wonderful. Unless they blow it against Baltimore. I'm just being silly. So, here's what I want you to do. Whatever you're doing, if you're watching baseball, if you're going on a walk, whatever you're doing, just let that idea brew in the back of your head. I have a graph coloring problem. How could I represent that problem where I can use a genetic algorithm to give me a good solution to it?
Actually, couldn't you visualize that maybe it's like a tree where you have like one color as your starting node and then you have another color, but you can define the tree and say that you can't have a child or a leaf be the same color as the parent?
Yeah, but I mean, we could use it where it's just a tree. I might not know what you mean, but like it's a graph, right? Like sure, the graph could be a tree, but remember, like we could have cycles.
Yeah.
All right, maybe think about it a little bit more, and then we'll talk about it next time. Yeah.
Representation, do you mean like the encoding?
Yeah, the encoding. What's the genotype? You know, and how can it get? What does it mean in the phenotype space? The reason I'm giving you this little assignment is we'll talk about it next time. Don't look up one. That spoils the fun. There's no hard, like you can be wrong, it doesn't matter. Maybe, I mean, it's kind of hard to be wrong. Remember, the representations, if it's workable, it's workable. But the reason I like this one is it might kind of require you to kind of flip how you think about the problem a little bit, but I don't want to say anymore. I might spoil the fun. Anyways. Yeah, all right. So let's carry on here. Come on. I think all like my Shift, Alt, and Function control keys have gone out of whack. It's quite annoying. Okay. And let's see. All right, cool. All right, so last time we were talking about different representations. We had like a Boolean one, like 0, 1, 0, 1 binary. We had like integers. And we also talked about continuous ones and which crossovers might work there, right? Where we're not like crossing over the values, but maybe we're affecting like what the real numbers are in the encodings. Now we're talking about permutation, inversion. You know, we were talking, these are mutations for a permutation strategy where we want our values to be unique. Inversion's a great one. You know, you pick it apart, you flip it, and you're good to go. You don't ruin the fact that it's a unique set of numbers. Now a little bit for crossover. The crossover for permutation representations can be quite tedious. And they're definitely more complex than the others, I would say. So the first one here is ordered crossover. Pick 2 points, copy the info between the 2 points to one child. Then Fill in the rest of the genes, the individual values, so like the following cities that weren't between the points, from the other parent only if it fits in order and loop back. Okay. Best explained with an example. I picked those 2 points, right? And so here's an example of one child. Right? So I take the first 2 points, and I copy all the values over to one of the children. Great. Then what I do is copy the rest of the numbers. So I want to copy, so it came from here. So now I go down here and I'm going to copy the rest of the numbers over. So I'm going to copy over a 1. Great. But if I try to copy over 4, I'm in trouble. Because there's already a 4. So all you do is you skip it. Then we loop back to the front. Copy over a 9. Cool. Copy over a 3. We're good. Copy over a 7. No, we skip it. Copy over an 8. And it might feel weird. If your first reaction is, but wait a minute, that's in the part that we copied over. You're right, but remember that part will be copied over to the other child. So it's fine. It's fine. It's fine. So then we can copy the 8, and then the 2, and then it'll all be filled in. So basically pick the 2 points, move it to the child, and then take the other cities in the other parent in order, but only add them to the child if it doesn't already exist in the child. And it could only exist in the child if it came from the other parents between those 2 points. This is not on the test. This isn't something you need to memorize. All you need to remember is that if you go to Google and you type in genetic algorithm crossover permutation, you'll find a bunch. Yeah, there we go. Partially mapped crossover, this is a good one. It's very similar. Pick 2 points, copy info between the 2 points to one child, put elements, okay, this is just, there. It looks terrible, but it's not that bad. So you pick 2 points, copy it over. Then, then what am I doing here? God, I gotta remember this myself. Jeez, this is brutal. So then I put step 1, the 2 parents, step 2. What on earth am I doing? So the 8, what? So the 8 goes where the 4 was from the other parent. Yeah, I know, right? Look, so we've got the 4 here. And now this is the value. So look, the 8 is in the same spot as the 4, but we find where the 4 is here, and then we put the 8 there. The 2 is where the 5, so then the 5, but then the 5's are, then we got a 7, so now we need to keep takeaway is, figure this one out later. Edge crossover, cycle crossover, there's a whole bunch. But as soon as you hit the permutation, it gets complicated, as you just saw. Because there's all of those rules that you need to make sure are there. Which one's better than the other? They're just different. Some might be more destructive than others. If I'm looking at these 2, let's say I'm looking at, which one is this one? Ordered crossover. If I'm looking at ordered crossover versus partially mapped crossover, does anyone have an intuition? Think of it in the context of TSP. And remember when I was talking about destruction, where, when the adjacency really matters, if I start messing everything up, that could be a big problem. So where adjacency is important, and the fact that this was followed by this, which was followed by this, might be very valuable information. If that all got jumbled up, that we might be in trouble. So based on order crossover and partially mapped crossover, which one would you, you don't need to be right, but your intuition, which one does your intuition tell you might be more destructive or less destructive? Second one, what do you think is the second one? More destructive. I'm going to agree with you, I think. Raise your hand if you're like, yeah. And the reason why I'm going to say that is look, when I take this contiguous chunk, okay, that's good, right? That contiguous chunk remains a contiguous chunk. That's important because that adjacency, that order matters. But then when I start copying over, I still maintain some amount of orderedness, where I follow these things like in order. And remember, with TSP, the starting city could be anything, so you could rotate this any way you want. It doesn't matter what is at index 0, right? But big hint for assignment 1, just make your starting city always index 0. Just keep it fixed, it'll make your life easier. But point being, the 1 gets copied over, and then the 4, but then the 9. So sure, we skip the 4, but there's still some orderiness to it. Where when you go here, partially mapped crossover, I don't even know what the hell's going on anymore. Things are moving all over the place, right? So that might give you a hint as to which crossover might be better. If someone on their assignment 1 implemented partially mapped crossover and also ordered crossover and maybe did a comparison, that's phenomenal. I have a feeling I know what the results are going to be. You probably do too. But that type of analysis would be fantastic on assignment 1. You know, if you do that, you do it well and you write it up well, that's like a 25 out of 25 points or whatever it's at. 25, 30, whatever, you know. There's a lot more. Okay, so now we're going to talk about genetic programming. Because genetic programming, in terms of what's popular in evolutionary computation, and all the algorithms out there, evolutionary strategies, genetic algorithms, genetic programming, yada yada, they're all important, they're all valuable. But evolutionary strategies, I believe, involves finite state machines, which are, you know, it's kind of peculiar compared to the other ones. But it's not as popular as something like genetic programming. Genetic programming is big, and I really like it myself. I use it a bunch. So, we can represent a lot of things with the tree structure, depending on how we want to think about it, but we can. So, like, I could take that mathematical expression, I could take that logic expression, I could take this little function here, or that little snippet of code, and represent it as a tree. Like, I can encode it as a tree. So here's an example of me encoding 2 pi plus x plus 3 minus y over 5 plus 1, right? Here's my encoding. Now, the choice of what's at the top, I suppose, is somewhat arbitrary. But I've got plus, and then I've got a minus and multiplication. So it looks like that's probably this plus. And then here I've got the 2 and the pi get multiplied together, and you add that to whatever the right-hand side of the tree is. Does this make sense? A lot of people, the first time they see this, you call it like an S expression or something. It can throw you off a little bit. But there is a one-to-one mapping between these two things. So the plus here happens to correspond with this plus. It doesn't necessarily need to be like, and any arbitrary function, what's the root? Doesn't really matter because we could just draw the tree slightly differently and it could still mean the same thing. So I guess it's not one-to-one mapping, but there is a mapping from this to what the expression means. So there's the plus, and on the left-hand side of this plus, we've got 2 times pi. That's this. And then on the right-hand side, we've got all of this. And what does this evaluate to? Well, we're subtracting, that's going to be this subtraction, the sum of x plus 3 from the division of y divided by 5 plus 1. I don't know why that's not just a 6, but whatever. There's an encoding for that expression, right there. And it's encoded as a tree. Here's that logical one. I don't know, the arrow. And then, oh, we're anding the x and the true. And then we're ORing the OR of x and y to, I don't even know what that is, but who cares? We can encode it as a tree. I could take that program, encode it as a tree. I can. And then, imagine for a second I'm evolving programs, how to program a robot to drive around and not hit anything. Like, you can kind of get a sense of like, oh, okay, so we can represent their programs as a tree. Right? Do we have any questions about this tree representation? So it's pretty cool. But now, because we've got a tree representation, it starts to beg the question, how on earth do we do our genetic operators though? Because we were learning about crossover, we're learning about mutation. Mutation might not be too bad. Does anyone have an idea about what mutation could be for something like this? Any wild guess? Because remember, any idea is workable, really, if it's workable.
Change the sign
Change the sign. So give me an example. Like change the...
from equal to maybe a minus.
Sure. Why not? So pick one of the nodes in that tree and change it. Is that basically what you're saying?
Yeah.
Perfect. That's a great one. Any other ideas?
Probably mess with some of the ordering.
You could mess with the ordering. Interesting. Like maybe do like a flip or something. Assuming that the operators work still. Like is it an operator that takes two values? So like the less than and equals, maybe, you know. Yeah.
Can you heapify it?
Heapify? That would probably be very destructive. But we're going to come back to that idea, because that's a very interesting idea.
Maybe don't do this in C++.
Well, yeah. So, I wrote a GP system in C++. No, first I wrote it in Java, and I wanted to make sure I got it right, because Java's a little more helpful when you hit run and there's a mistake. And it goes, you made a mistake right here. C++ will be like, yeah, it totally worked. Meanwhile, it doesn't. So I wrote it in Java, then I wrote it in C++ after, and then I just went back to the Java one, because I hated the C++ one so much. Anyways, another mutation might be pick a node and maybe replace the whole subtree. That could work. It's definitely more destructive, but it could work. Crossover, that might be a little bit more difficult, but like with evolutionary computation, a lot of times we might have a fixed chromosome length. TSP, well, there's that many cities as you need. With the trees, they can be like arbitrarily large, right? They can just get bigger and bigger and bigger and bigger. And we'll come back to this. There's this idea of bloat that we can talk about. But the trees can be weird shapes and get really long. So symbolic expressions, S expressions, are defined with a set of terminals and a set of functions. And can be non-typed and typed. Okay, so perhaps the most accessible and easy to play with style of genetic programming is something we call symbolic regression. Raise your hand if you're familiar with linear regression. A couple people, great. So linear regression is fantastic because, I mean, and there's some variations on it for like regularization, but let's not worry about that. Linear regression is basically, I've got all these points, you know, great. So I have all these points and it's a two-dimensional thing. And raise your hand if you know how to draw a straight line. Of course you do. You do this. Right? Or if you like more algebra-y, you could do like y equals beta x plus some constant or something, right? But it's the same thing, right? So in order to draw a straight line here, I need to know where the intercept is and what the slope is. And if I want to do something called linear regression, there's some simple mathematics that I can run that is guaranteed to give me the best line to fit this data. It's perfect, it's great. Right? I don't know, looks like we're lucky, we go right through the origin. Assume that that's the best line. Great, cool. And with linear regression, you can add more dimensions, so imagine it's like 3 dimensions, and now you're not just drawing a line, you're kind of drawing. But the point is, it could be a line still, but the point is, we have a strategy for doing something like this. But we run into a bit of a problem when, what if the data points we have look something more like this? You know? And I tell you, okay, tell me the straight line that best fits those data points. I don't know, I'll go like, Does that look very helpful to you though? No. Because a lot of the times the point of drawing the straight line is, I can expect where any new data point coming in would be. It'd be kind of around here. Where here, it's not very helpful, is it? It's just kind of cutting it there. So, who knows what we could do in this scenario?
Do nonlinear regression?
Yeah, so how could we do nonlinear regression? All right, that's a good question. Does anyone know what trick we could do here? There's two easy tricks that are basically the exact same thing.
You could do like a Spearman or a Pearson coefficient test.
Okay, there's that, but that's not quite where we're going here. So one thing you could do is you could say, well, what if if I know my data looks like this, I can do the regression and I can kind of modify my space to pretend that it's actually a straight line. Like I could go in and say, okay, so I have okay, here's the easiest one. Here's what I would do. I've got a whole bunch of x and y points, right? X and y's, right? And clearly this is like parabolic, right? We know that. If I have all these points, the issue is I want to know what this looks like such that that's true. Well, one thing I could do, because I know it's parabolic, I know there's going to be like a squared in there. So what I can do is actually just go to all these x's and square them all. And then do the regression, and then it can fit it, right? So we just kind of like change what the space looks like. But this becomes problematic when the data points you get that much more complicated. And maybe I print it in 2 dimensions and go, okay, I have no idea what the function would look like to fit that. Here, it's obvious. It's like parabolic, right? I know it should look something like this, right? But linear regression can't, out of the box, do that for you. So if I come here and I have some data points, I realize this marker's getting hard to see, that look all right, fit that. Right? You're going to go, well, what? Right? Totally just destroyed this marker.
Yeah.
And I go, oh, that's the obvious, right? The line's like this. Right? Yeah, see, it's great. That line is perfect. But the problem is that function doesn't look like this, does it? That function's going to have some like squareds, maybe even a cubed in there, I don't know. And this is assuming it's in 2 dimensions and I can plot it and get a sense of what it is. What happens if I have like 30 dimensions? And then someone says, oh, just plot it and get a sense of what the function looks like. And then what do you say? How the hell do you plot 30 dimensions and get a sense of what the hell that space looks like? Right? Our brains don't work that way. So, what if I told you, just use genetic programming, randomly come up with a whole bunch of functions. How well do they fit the line? They're going to suck. But basically think of a GA and just do that over and over and over, and at the end of the day, you'll get some pretty awesome functions. And then there's typed and non-typed. An example of a non-typed GP would be something like symbolic regression. I don't like the name. They call it non-typed or no-typed. Because it's one-typed, where all the values are the same type. So with symbolic regression, they're all like numbers. But, excuse me, if I have something like this, we can see like, well, this gets evaluated to like a Boolean, and these are numbers. So now we suddenly have like a tree that might have multiple different types in it. It can get a little bit more complex. Anyways. So mutation, select a node and change it. What did I do here? Oh, I replaced that whole thing with just Y. Wonderful. There's a mutation. It'll work. Crossover. Select two subtrees, flip them. So I took this subtree and this subtree, and then I took that multiplication and replaced it here, and then I took all of that and replaced it with this part right here. There. Pick two subtrees and swap them. And there we go. Any questions about that? We're going to learn a lot more about genetic programming. I love genetic programming. I think it's a lot of fun. Symbolic regression is a really interesting problem. Even though it's like the simplest version of GP, arguably, it's really powerful because a lot of times in the world, we really care about getting a nice, simple, closed-form mathematical expression that looks, just like a regular old function you've seen that could describe some complex process. We like that a lot in real life. I could, imagine for a second, I tell you, so you figure, I don't know, Isaac Newton was there dropping a bunch of crap and calculating how long it took to fall, and then after all that time, those brilliant physicists came up with the expression to describe like acceleration due to gravity, and like how long it'll take, right? Simple stuff, but whatever. They came up with that. So, there we go. It's defined, great. And they did that by observing the data and, thinking, how can we do that? Well, if we lived in a universe where Isaac Newton didn't exist, but we knew there was something going on here, I could just keep doing this over and over and over, record the results, how high was it, how long did it take. If I just pump all that data into symbolic regression, it'll just tell me the answer. It'll find that function for you. If not the exact function, it'll get you a function damn close to the real function. And sometimes even getting the exact function doesn't really matter, as long as it gets you close enough where you go wait a minute, look at that. And then you can change it a little bit to be exactly what you need it to be. Symbolic regression is amazing. I like it. And what's really cool about symbolic regression, because it's non-typed, there are a couple of really cool tricks you could do to it that you can't in multiple typed GP. There's a couple of really interesting hacks you can do, namely with the representation, that can really make it so much better. When I wrote my genetic programming system, it was designed strictly for symbolic regression. And you might remember I was saying, if you're doing genetic programming, often you make your population small, you set the number of generations small, because it just takes forever to run. And if you choose to do the genetic programming assignment, I recommend you use this library called DEEP, Distributed Evolutionary Algorithm Parallel, even though the parallel part's totally not really true, but it's this Python library where it makes it really easy to do. And then when you do it, you're going to see it takes a long time to run. But my GP system designed for symbolic regression, I could set it to run for a bajillion generations and have gigantic populations, and it would still, it would run better because of all these little hacks that I was able to do. One of the brutal things about the tree representation is something called bloat. And there's a couple of different versions of bloat, but you can imagine if I start with two trees like that, imagine I get really unlucky and I picked this subtree and this subtree. Suddenly this tree on the left got really big, right? And I can keep doing that and those trees can start to grow really, really, really big. And the bigger they grow, the longer they take to evaluate. And the bigger they grow, the more likely we are also going to have really useless chunks of the tree. It can often happen where you've got some I don't know, a couple of nodes over here that are really important. Then you might have this gigantic subtree. That at the very end of it, it does all those calculations. And at the very end of it, it does like times 0. So after all those calculations, all of this means 0. That's bad. So anyways, we'll talk about bloat a little later. I'll see you later.